Okay, so one of the things that I want to talk about, well, really the only thing that I want to talk about in this video is an existence and uniqueness theorem for the linear PDEs that we've been looking at. Before I do that, I want you to pause the video. So I want you to think of all of the things we've done so far. I want you to pause the video, though not now, after I get done saying what I'm about to do, and I want you to try to solve this equation here. The t derivative of u minus the x derivative of u is equal to 0, and u of x minus x is equal to x. Okay, so we're looking on the line t equals minus x. We know that, on the line t equals minus x, u is equal to x. I want you to try to solve this equation, and I want you to do that before you watch the rest of the video. So it's I think conceptually it will be very helpful if you attempt to solve this problem before you watch the rest of the video. So I hope you pause it as I'm erasing, and then start back up again once you've done that. Okay. So what we're gonna do now is let me find the statement of the theorem here. So let me state the theorem. You know what? I just realized there's a typo in the notes. Hold on. Let me fix that. Definition 5.8 should be a theorem. So if you're looking at an older version of notes, it'll say that. I will try to update that today. But we have this problem here. We have a times the t derivative of u plus b times the x derivative of u is equal to c. And c is allowed to depend on x and t and u. A and b can only depend on x and t. In other words, a and b do not depend on u. Now, I have been calling these linear, and I will continue to call these linear. Semilinear is a better term for that, because c here, it can depend on u, and it can depend on u in a nonlinear way. So overall, it's not a totally linear equation, but since this part right here is linear, if a and b are only functions of x and t, it's a linear equation in the u variable. The left-hand side is linear in u. Because of that, I sometimes will call it linear. All right, and then we've got u restricted to some curve is equal to some given function here. Now, let's think through the way that we have been approaching these problems. We've set up a system of characteristic equations. Actually, let me begin by reminding you that we typically parameterize the curve gamma with something like, I'm going to call it x naught of theta, t naught of theta. This just gives us x naught and t naught. These are functions, so x naught of theta, t naught of theta. This parameterizes a curve in the xt plane. So let me just kind of schematicize this a little bit, because I'm going to be using that. Actually, I want to use this part of the board for part of the discussion, so I'm going to move over to the left here. So this is x, this is the t-axis, and then we have some curve gamma like this that is parameterized by this curve here. So what we can do then, for every parameter value, we get a different x naught of theta, t naught of theta, and we have been setting up a system of differential equations. X prime of s is equal to a, with x of 0 equals x of theta naught. T prime of s equals b, x prime is equal to b. T prime is equal to a, with t of 0 equals t of theta naught. And then z prime of s is equal to c. And here we have z of 0 is equal to u of, not theta naught, I don't know what I'm doing theta naught, x of theta, t of theta. So let me just step back, because I had a theta naught there and there. So we have this system of differential equations. X prime is whatever is multiplying the x derivative. T prime is whatever is multiplying the t derivative. And then z prime is going to be the right-hand side, and we have the corresponding initial conditions. So then what we've seen then, is that for every theta value, we can solve these two equations. For every theta, we can solve these two equations without worrying about z at all. That's important for this. We can solve x and t without referring to the z equation at all, and we get these curves that go through this curve here, gamma, and for every theta, that is for every parameter value theta, that corresponds to a different point on the curve, and we get these curves right here that we called characteristics. We do one more. Okay, and then we found these curves by solving that system of differential equations just for x and t. And then what we did was we solved the equation. We picked a value of theta here, for example, and solved this equation. And then this is going to be the value of the solution along the curve. Okay, and then to actually get a formula like for u of xt, how did we handle that? Well, we imagined taking some arbitrary point here and then solving these two equations for this point here, or plugging this point and solving these two equations for s and theta. And essentially, this just tells us, by finding out what the theta is, that tells us which characteristic curve we're lying on, and then s tells us how far along we are on the curve, and from that we're able to solve the differential equation. So I want to talk about existence and uniqueness theorems. And I want to ask a question here. I want to try to think about what could go wrong. So here's some things that could go wrong. So let's say I've got this blue characteristic here, and let's say it goes up like this, and then I have this purple characteristic, it goes up like this. Now we have a problem. That point right there, where they intersect, that lies on two different characteristics. So when I find the corresponding theta and s value, do I get that theta and the corresponding s, or do I get that theta and the corresponding s? There's some ambiguity there. That would be a problem. The opposite problem would be, what if I have a point here and all of the characteristics miss that point? In other words, it's not on any characteristic. What if you have characteristics that kind of look like this, and none of the characteristics actually hit that point there? What are we going to do there? If there's no characteristic at all that passes through that point, again, what is the characteristic? Or what is the solution there? Because it doesn't lie on a characteristic, but our technique relies on the fact that it does lie on a characteristic. We could have a similar problem. We could have a curve. What if the curve kind of goes over on itself? Now, this is like one characteristic. It's different from this purple and this blue. These are two different characteristics that intersect here. This blue one is kind of like the same characteristic. It's the same curve. So is the theta value this theta value with the corresponding s value, whatever it needs to, going from there to there, or from here to here, or is that the corresponding theta value that we need to use when solving the differential equation? So there's some ambiguity there. So the two main problems here are, maybe there's a point that does not lie on any characteristic, or maybe there's a point or points that lie on several characteristics. So maybe there's some points that lie on no characteristics. Maybe there's some points that lie on too many characteristics. So this curve here kind of has two different thetas. This is kind of like it lies on two different characteristics. If you imagine one characteristic starting there and one there, but then this is really like legitimately lying on that point there, kind of legitimately lies on two different characteristics, because these are two different curves that are passing through each other. Okay, so whatever the existence and uniqueness theorem is going to be, is going to have to account for that. It's going to have to somehow have conditions in the theorem that makes that not able to happen. Okay, so now we can talk about the theorem. So the statement of the theorem is going to have to guard against these two possibilities: the possibility that a point doesn't lie on any characteristic, and the possibility that a point lies on too many characteristics. So here's how we're going to think through this. So I want to schematicize this again. So this is going to be the xt plane, and we're going to look at our curve gamma, and we're going to assume that gamma has a parameterization x naught of theta, t naught of theta, like this. Okay, now based on the existence and uniqueness theorems from systems of differential equations, we know if I fix a theta here, let's call it theta naught, if I fix a theta naught there, then there's going to be, obviously theta naught is not the point. The point is x naught of theta naught, t naught of theta naught, but we can just Think about it, think about theta. This parameterization is giving a coordinate system on this curve here, which is a good way to think about this stuff in general. But at any rate, what the existence and uniqueness of this system of equations here says, this is just the ordinary differential equation theory, it says there is going to be some neighborhood on theta naught on which there is a unique solution to this system of differential equation for every initial value. Okay, so for then every theta that we put here in some interval around theta naught, we're going to get a unique solution. In other words, we're going to have these curves, and these curves are going to be characteristic curves. And what it says two things. One, for every value of theta from that point to that point, there's going to be a characteristic emanating from that point. And two, they're never going to intersect with each other. Okay, so what this means, I like to think about it in the following way. We have this curve, imagine it's flat. These characteristics are going to kind of be like bristles to a paintbrush, but they don't have to necessarily be going straight up. They can kind of be going, curvy directions as well, which is why I drew them curvy here. Okay, so the characteristics correspond to paintbrush bristles, and actually they go below gamma as well. Okay, so what we want to happen then, or what we want to make sure, the following two things happen. We want to make sure these, paintbrush bristles, these characteristics, like legitimately go up into the area above gamma. Okay, we want to make sure they legitimately go up into the area above gamma. So if you think about a paintbrush, if you have paintbrush bristles that are bent over and are sideways, you're going to get a gap in the paintbrush, and so when you paint, there's going to be a gap. Well, that's that corresponds to points in the plane not being hit by characteristics if you have the paintbrush bristles bent over. Well, mathematically, the paintbrush bristles being bent over means the tangent vectors of these characteristics are parallel to the curve. But the tangent vectors to these bristles, to these characteristics, are just the functions b and a. So what we want to have happen then is we want to ensure that the vector BA is never going to be parallel to gamma. This is called the non-characteristic condition. And so here's a definition. If BA is never parallel, if BA is never parallel to gamma, meaning this vector being parallel to the tangent vector gamma, if BA is never parallel to gamma, then gamma is non-characteristic. Is non-characteristic for the PDE. Okay, kind of, if you want to think about this, sort of a great geometric description, but one that's kind of more algebraic or something like that, we want to make sure that B, okay, so B is a function of x and t. So we want to make sure a couple things. I want to sort of expand the way that we're thinking about x of s and t of s. So I want to think about it in the following way. I want to think about it as x of theta s and t of theta s, because these solutions depend on the parameter theta. We get a different curve for every theta, and it's going to be helpful to denote that that dependence explicitly. So what's happening then, b of, sorry, let me move over here, b of x, if I plug s equals 0, I get theta 0. Then the next component is going to be a of there's too many compositions here. B of x of theta s equals 0, t of theta s equals 0, and then same thing with a. It's going to be, I'm going to write it down and move out of the way, a of x of 0, x of theta 0, t of theta 0, like this. Okay, so what I just wrote here, what I'm writing here is this is going to be the vector be A, and then evaluate it at the point when for some particular value of theta and where s is equal to 0. Okay, but b and a are both functions of x and t. T and x are both functions of s and theta, so there's a lot of compositions going here. This is b of x of theta 0, t of theta 0, comma, a of x of theta 0, t of theta 0. All this is just this vector field BA evaluated along the curve gamma there. So I'm going to erase this. So what we want is sort of algebraically, this statement about never being parallel means that the vector BA evaluated at some theta and s equals 0 is not equal to a multiple of the tangent vector to gamma, which is x naught prime of theta, t naught prime of theta. That's what we want to look at here. Okay, so we got a lot going on here. You might have to pause to think through some of this. I don't know if I've said it already. I've attended this video a couple times now, and I keep getting little details, not exactly how I want, but I'm just going to kind of leave things here now. There's just a lot of notation and composition. I can't really do a lot about that. X of theta is 0, x of theta s, t of theta s. Let's think about this. Let's say if s is equal to 0, okay, what we get, if we look at this parameterization, x of theta 0, t of theta 0, well, remember what x and t are. They are solutions to these equations here. And when s is equal to 0, x of 0 is equal to x of theta, t of 0 is equal to t of theta. There should be an x naught and a t naught there. So if s equals 0, x of theta 0, t of theta 0, this is just exactly equal to the parameterization for gamma. So this is x naught of theta, t naught of theta. Okay, so that's what we get when s is equal to 0. If you look at the solution to this system of differential equations here, when s equals 0, we just trace out the curve gamma. Okay, so another thing that I want to look at is this function, x and t. This induces a function from the st plane to the xt plane. So what I mean is the following. So if I define this function, f of theta s is equal to x of theta s, t of theta s, this gives me a function from the theta s plane to the xt plane. So let's say if I want to sort of map this point theta naught over here, I get theta naught. This is the theta axis. This is the s axis. Okay, so what I know, again, let me back up. What I know from the existence and uniqueness theorem for ordinary differential equations is that if I look at some neighborhood around theta naught, I know for all of the thetas going from there to there, there's going to be a unique solution to this differential equation. So in other words, I know there's going to be, for every theta between that and that, there's going to be a characteristic curve like this. What I need to make sure of is that every point in that neighborhood around theta naught, that is, every point in this neighborhood here, lies on exactly one characteristic. And the way that I can do that is I want to ensure that this function here is a one-to-one function. So what I mean is the following. If I look at a neighborhood around theta naught here, theta going from that point to that point corresponds to this blue line right there, that blue line segment right there. And then s increasing from some negative number to some positive number is going to correspond to s just going up like this. Okay. So now what I know is that in this ball, every point in this ball is going to lie on exactly one of these vertical lines here, and I want to show that the function going from here to there is one-to-one. And that means every point here, there's going to be a unique s and theta. For every point there will be a unique s and theta. meaning there's a unique characteristic on which the point lies. Okay, well, how can we do that? Well, we're going to use the fact that locally, if I know I'm going to take the derivative of this, it's going to be a matrix. If that matrix is non-singular, it means locally this function is going to be one-to-one and onto, going from that point to that point. Okay, so let's go ahead and convert and compute what this is going to be. So if we look at the Jacobian determinant, or the derivative, it's going to be a matrix. What we're going to get is the following. The top left entry is going to be the derivative of x with respect to theta. So we're going to get the derivative of x with respect to theta, like that. This entry here is going to be the derivative with respect to s of x, like that. This entry here is going to be the derivative with respect to theta of t. And then this entry here is going to be the derivative with respect to s of t. Okay, now what we want to do is we want to plug in the particular point, that point there, that theta naught point there, this point here. Okay, the ball kind of made it less clear about what I'm referring to. So that point corresponds to theta naught being whatever it is, and then s is going to be equal to 0 because we're on the s-axis. Okay, so what we're going to get then is the following. If I just make these replacements, wherever I see a theta, I'm going to put a theta naught. So let me do that first. I'm going to get a theta naught here. I'm going to get a theta naught here. And I'm going to get a theta naught there. And then I'm going to put an s equals 0. So s equals 0 is going to be that. S equals 0 is going to be that. S equals 0 is going to be that. And s equals 0 is going to be that. Okay, now remember the s derivatives of x and t. Those are just the derivatives like going up this way. And when s is equal to 0, for a theta naught, we have the s derivative of x with respect to theta is going to be b, where b is equal to, the theta value is equal to theta, and s is equal to 0. So it's going to be like this b right here for that theta, and s equals 0. I'm going to use similar notation. So it's going to be b when theta is equal to theta naught, and s is equal to 0. So in other words, this notation here means b of x of b of x of theta naught 0, comma, t of theta naught 0. So it's too much room. I can't, there's not enough room for me to write that. And then this right here is going to be similar. This is going to be a. Theta equals theta naught, s equals 0. Because remember, these were the derivatives with respect to s, but that's exactly what b and a are. B and a are the derivatives with respect to s. Okay, now over here, what we're going to have, this is the derivative of x with respect to theta when s is equal to 0. Well, if s is equal to 0, we're just looking at the parameterization of the curve here. So what this is going to be x naught prime of theta naught, and this right here is going to be t naught prime of theta naught. Well, this is exactly, so this matrix is 1-to-1. In other words, the columns are linearly independent. Or sorry, what does it mean for this matrix to be 1-to-1? By whatever theorem you want to appeal to, it's 1-to-1 if and only if the columns are linearly independent. But what does it mean for the columns? If you have two columns of a matrix, what does it mean for them not to be, what does it mean for them to be linearly independent? It means they're not multiples of each other. So this matrix being 1-to-1 is equivalent to this condition here. Okay, so let's back up. What we've proven is the following. If we have a linear PDE, we have a curve gamma here, we fix some theta naught, by the existence and uniqueness theorem of solutions to these two differential equations here, we know there's going to be a unique characteristic, that is a unique one of these curves, through every point going from some theta value that's smaller than theta naught to some value that's bigger than theta naught. the general existence and uniqueness theorem doesn't tell us how big that interval is. It could be small. We just know on some open interval around theta naught, there's going to be a unique, there is a unique solution to this system of differential equations. Okay, so what we want to do then is we want to make sure that every point in some neighborhood around theta naught is going to be on one of those characteristics. That's what this whole argument is over here. These two functions here, x of s, t of s, depend implicitly on theta. So if we just denote that dependence explicitly, this gives us a function from the theta s plane to the xt plane. If this determinant is 1-to-1, that is, if these two columns are not multiples of each other, it means that the map locally is 1-to-1. In other words, there's some neighborhood around theta naught that gets mapped in a 1-to-1 fashion to some neighborhood around this point right there, and vice versa. So 1-to-1 and onto is what I should be saying here, a surjection. So the determinant being non-zero is equivalent to the columns not being multiples of each other is equivalent to this matrix being 1-to-1. A number of different ways to say it. This matrix being 1-to-1 near theta naught, or at theta naught, says that there's a neighborhood around theta naught, or around theta naught, theta equals theta naught and s equals 0, that is 1-to-1. In other words, for every point in this neighborhood here, for every xt point here, there's going to be a unique s theta over there. But when there's a unique s theta, that just means we can do the thing about solving this equation uniquely for s and theta. If we have x equals some function of s and theta, t equals some function of s and theta, we can solve that uniquely in principle for s and theta in terms of x and t. Okay, so now that we have established that every point in some neighborhood around theta naught lies on a unique characteristic, now we can just use the fact that there is an existence and uniqueness theorem to equations like this. So C can depend on x and t and u. We've solved for x and t. So really at this point when we solve for z, it's really just like C depends on s and u. And so now what we have is just one scalar valued ordinary differential equation, and we can apply the existence and uniqueness theorem there to show that along each one of these characteristics there's going to be a unique, there exists a unique solution to this differential equation along each one of these characteristics. Okay, so then we know that for every point on that equation there's going to be a unique solution, and we know that, for every point on a given characteristic there's a unique solution to this differential equation, and we know that every point is on exactly one characteristic. Okay, so what we've proven, so I want to be careful about what we've proven so far. The argument that I've given so far shows that if all of this is true, the method of characteristics produces a solution. It doesn't quite say that solution is unique. So to say the solution is unique, we need this other fact, which says that if a solution satisfies this equation here, then it's also going to satisfy these characteristic equations. Okay, so in other words, if a function satisfies this, this problem there, then it's also going to satisfy these characteristics. And there's a unique solution to this set of characteristics based on the argument that we've given and based on just using existence and uniqueness theorems for ordinary differential equations. All right, so let me actually state the theorem. So all of this sort of indicates, that we're not going to have a global existence and uniqueness theorem. It's only going to be a local existence and uniqueness theorem, because all we showed was that there's some neighborhood around theta naught for which there is a unique solution to this problem there. Theta naught is generic, so something is going to be true for all theta naughts. So let me now state the theorem. In the notes it says definition 5.8. That should say theorem. I will fix that. So if A, B, C, and G are all continuously differentiable, and gamma is non-characteristic, Okay, so in the context of this problem right here, if A, B, C, and G are all continuously differentiable, and let me just remind you, A and B depend on X and T, C depends on X, T, and U, G just depends on theta, so the value of U is along the curve. Okay, so if A, B, C, and G are all continuously differentiable and gamma is non-characteristic, then there exists a unique solution on a neighborhood. I'm going to abbreviate this as NBHT, on a neighborhood of the curve gamma. Okay, so this says on a neighborhood of the curve gamma, there exists a unique solution. Okay, so I just want to explain what that means just briefly here. Okay, I won't really call it a proof because I was missing a lot, but the sort of argument that I gave for this part here says that for every theta naught, or says for a fixed theta naught, there is a ball around that on which there is a unique solution. Well, now what we're going to do is we can just apply this same argument to any theta naught. Maybe sometimes we'll get a great big ball, and maybe sometimes it'll be small. But what we're going to do is as we take the union of these balls, as theta naught goes, runs through the parameter domain, it says that there's going to be a neighborhood around theta on which there, a neighborhood around gamma on which there is a solution. So, you might get something that looks like this. Let's say this is X, this is T, this is our curve gamma, and then we get some neighborhood like this. Maybe it gets really, really close to gamma at some points and then farther away in others. In this neighborhood around gamma, that is in between these dashed curves there is a unique solution to this PDE. Now, the theorem doesn't tell us directly about how big the neighborhood is or anything like that. It just says on a neighborhood of gamma there's going to be a unique solution. Okay, I know that was a lot. Think through what I talked about here. Used a bunch of different things that you might not be familiar with or have forgotten about. But I hope you'll think through it and like it.